We're starting Chapter 4 with Section 1. And again, I want to repeat the idea that you're watching the lesson in an earlier video when I'm at the blackboard or the whiteboard, and then going through all of the exercises. And then this would be supplemental to that. But I will do a little review as we start right now. Actually, my diagrams here are better than I had on the previous lesson because I have this nice line tool. But you can see here that we have an equation that we'll call equation 1 in standard form. And here we have equation 2 in standard form. And since these are the sub 1s and these are the sub 2s, we're assuming they're different equations. Now, if I graph this equation by using the x and y intercept or solving for y, and if this is equation 1, that's this line. And then if I graph equation 2 by whatever technique, and I get this line, an interesting thing happens right over here. And you say, what's happening? Well, they're intersecting. And as they intersect, the ordered pair they intersect at, interestingly, is a solution for this equation and this equation. Their intersection assures us of that. So this is a case where the equations are independent, but it is consistent in that you have one solution, at least one. Now, if I graphed equation 1, this would be a different equation, of course, and it's this line, and I graph equation 2, and it's this line, I see that are these ever going to intersect? And the answer is no. And what's going on here? Well, the lines are parallel, so there are no solutions. And we say these equations are independent, but they're inconsistent because you have no solutions. Now, in my next example, if I were to graph equation 1, and I don't know if you could see it, but it's a red line there a little bit, and then I went to graph equation 2, and that's the green line, and lo and behold, it's the same line. Now keep in mind there are arrows on these lines, and since you have a set, even though they appear different, they are the same. So whatever solution would be for the green line as an ordered pair would be a solution for the red line as an ordered pair. And how many solutions do they have along this line? Well, there's an infinite number of solutions. And you write the answer to this as saying there's an infinite number of solutions, or they sometimes will give it to you in set builder notation. They'll say x comma y is such that it's one of the equations, because the other equation is the same. It's just disguised. And here, the system of equations are dependent in that they're the same line, one is the same, and they are consistent. So here you just have the one solution. Here you have no solutions, and here you have an infinite number of solutions. So this is the background. I'll leave that up a little bit, and that's something you should be aware of as we do all of the lessons in Chapter 4. But here what they're wondering is whether an ordered pair satisfies the system of linear equations. So what do we do here? Well, here what we're going to do is substitute in there the various values. So this is going to be a negative 2 for the x, and this is going to be a 1 for the y. And this is going to be a negative 2, and this is going to be a 1. Now, 2 times negative 2 is negative 4, and this is a negative 4. So this checks. And for the second equation, this is going to become a negative 1, and this is a negative 1. So this checks. So this is the procedure you'll be using. You substitute this for the x value, substitute this for the y value, and see if it makes a true statement. And for our first 4, it's going to be yes, as we found out for this one, no for number 2, no for number 3, and yes for number 4. I'm not going to do all these, and I can see this one's a little tedious here. Now, for these, they're asking us to solve each system of the equations by graphing. And notice they're both in slope-intercept form, so I will plot my y-intercepts first, and then from my y-intercept the slope. And I'll do the same thing for these because they're both in that form. Now, it did take me a little bit of time to graph these, but let's go over it. A negative 1 is right there. My slope is 2 over 3, so I go over 3 up 2. Then I do my 4, and I change colors to blue. There's my 4. And it's a negative 1 slope, so negative 1 over, negative 1 up. Negative 1 over, negative 1 up. And then notice it intersects right on the grid line. And what is this point? Well, it's 3, 1. Now, when I did these the other lesson, remember I was sketching. Here it's nice to have graph paper, and when you do it on your math lab, you're going to use your tools and plot out 2 points, and then a nice line forms, and then you ought to pick it out pretty well. All right, for number 6. Now, as we look at this, here's my y-intercept is a positive 1. So with blue, there's my positive 1. And then my slope is a negative 2 over 1. So I went left 1, up 2. And my other one is a, change colors, negative 5, right down there. And the slope is a 1. Now, an interesting point, you might have picked this up, if it's 5 here, it's going to be 5 there. So 5 over, 5 up, that's 1. And it gives you a little greater ease at plotting the point. So what's our ordered pair here? Well, it's going to be over 2, down 3. So 2, negative 3. And again, you're using your graphing skills from an earlier section. Again, going over the graphs with you, a negative 3 is in red. I'm going to go over 2 up 1, over 2 up 1, and there's my line in red. And then now in blue, negative 1 right there. I'm going to go over 2 up 3, over 2 up 3, and I also went over 2 down 3 to get another point, and there it is right there, our point of intersection. So we're going to go over 2, so that's a negative 2. And we're going to go down 1, 2, 3, 4. Negative 2, 4 is these equations again are independent, but they are consistent in that they intersect at this point. All right, the key to number 8 is that it's in standard form. So I wanted to solve for a positive y. So I brought the y over, brought the 3 over. So now there's my y-intercept, and my slope is 2 over 1. This is just going to be a vertical line. So my ordered pair then would be for my x is a -1. And my y is going to be, let's see, 1, 2, 3, 4, 5, 6. -6. For this one, again, it's in standard form. I have to solve for a positive y. So I transpose the the positive 2x. It became -2x. Divide everything by 3. I now have my y-intercept as 2. My slope is over 3 to the left, up 2, and then down 2 over 3. There's my point, and x equals 3 is a vertical line. So my ordered pair now is 1, 2, 3, and that happens to be our y-intercept there. Okay, here we brought the y over. My y-intercept is a -1. My slope is over 1 up 3, and my other line is y equals -4, which is a horizontal line. So it intersects right there, and this is over 1, so that's going to be a -1, and that's going to be a -4. Okay, again, we're running a little long, but a lot of good stuff here that we're using from chapter 3. So as we look at these, we see that here we had to solve for a positive y, transposed it. So there's my y-intercept, there's my slope. Here I had to transpose the 4x, became a -4 divided by 3. And when I drew the lines, they intersect at this point. And I did the same for that. I see it's around 12 minutes, and this is going to be a long tape, but this was quite a doing all these graphs, solving it, putting it in a form that I could graph it, and then trying to be accurate. And the point here is 2, -2. Again, the graphs are independent, but consistent in that they have at least a single answer, a point of intersection. This next one's a little different, so let's take a closer look at it. Here I'm going to transpose the -y over to this side. I get a positive 2y. Bring over the 2, I get a -2. Divide everything by 2. And then I see here that I have my slope is 1/2. My y-intercept is a -1. And I wrote it this way. And you might say, well, wait a minute. I have this equation and this other equation. They are the same. So let's just graph it. We're going to put a dot on -1. Goes over 2 up 1. And then do the other one. A dot on -1 over 2 up 1. It's the same line. So, what will our solution be? Well, the graphs are dependent because they're the same, and they are consistent because for this, the answer is infinite number of solutions. Or another way to write it, in we call it set builder notation, is you put a brace and you say x comma y is such that x minus 2y equals 2. And these are the same equations. This is in standard form. This is in slope-intercept form. Now let's do 16. So again, as we look at example 16, they're both in standard form. Well, this one's in standard form. This one is the start. I had to move this over. And I'm solving for a positive y. Now when I do, I get this. And when I solve for a positive y in the other equation, I get this. And lo and behold, they're the same again. So this is infinite number of solutions. I'm not going to graph it. You may have to graph it in your lab, but again, we've done a lot of graphing. Now the key to these is to solve for a positive y and then graph. All right, now as we look at number 17, our first equation is in slope-intercept form. And as we solve equation 2 for a positive y, now I just transposed the 3 over, left that as a negative. But now I'm going to divide through by a negative. I see, look at, the slope is the same. The y-intercepts are different. So if I were to graph these lines would be parallel, and there is no solution. Writing that with my mouse. So in number 18, I just rewrote this, solving it for a positive y equals that, and this becomes negative on the other side, but I wrote it this way. And here I solved for a positive y here by transposing this, getting a negative 2x plus 2. And now to get a positive y, I have to divide everything by the negative 5. That's with the y. So I get a positive y equals this. Notice again, the slopes are the same, but the y-intercepts are different. So the lines would be parallel. And for this, there would be no solution. Now, if you follow baseball, Babe Ruth was one of the greats, and so was Hank Aaron. So in what year did Babe Ruth and Hank Aaron hit close to the same number of home runs? Well, you're looking about right there where they intersect, and that's about 6. So the 6th year. In which year did Hank Aaron hit the most home runs? Well, Hank Aaron hit the most home runs in the 4th year. Here he is there. Drop it down. Okay, and that wraps this up. We'll now go to other methods of solving these systems of linear inequalities. And we ran just close to 18.